Density. Today we're going to expand on what we already know about density and how the concept of density applies to different physical quantities and shapes. By the end of today's lesson, you'll be able to define different types of densities and understand the meaning of the phrase per unit blank in terms of physics. So starting with the big idea of density, it tells us how much of something is packed into a space. In our case, we usually think about mass packed into a volume. That's what we learned in chemistry, that's what we learned in middle school. But it could also be charge or even current. Imagine two staircases. One is full of clothes but light, and the other is packed with heavy tools. Which one is denser? Density helps us make this comparison mathematically, and it's an idea that appears everywhere in physics. There's a special phrase that you will come across that is uniform density, and that implies that the density is the same for each individual section of the object in question. If we chop up this ruler, plastic ruler, each one of those pieces are going to have the same density no matter if it started at the 0-inch mark or the 7-inch mark. Non-uniform density implies the density is not the same. If we chop up this hammer, the density is going to be much greater at the head of the hammer than it is at the handle, where it's made out of wood. Key idea here is it's an intensive property that is independent of the system's size. In physics, we say something like per unit time or per unit length when we're describing a ratio. Think of it like a recipe. How much mass per cup of volume? For example, when we pour sugar into a measuring cup, the mass per unit volume tells us how tightly the sugar is packed. This concept helps us compare systems of different sizes. It doesn't matter if it's a giant sugar bag or a teaspoon. Density stays the same because it's a ratio. This is useful in other areas of physics, as we'll see throughout this year. Free baking tip before we go on: don't use volumes for measuring ingredients. Use mass. So get yourself a kitchen scale. So an example of per unit whatever. We have mass per unit volume, that's volumetric density. Mass per unit length, that's linear mass density. Charge per unit length, that's our linear charge mass density. Or excuse me, linear charge density, that's a typo. Charge per unit area, surface charge density. Change in distance per unit time, that would be a speed. This ratio is going to give us a clear understanding of the distribution of quantities in physical systems. Volumetric density, or rho, the Greek letter rho, tells us how much mass is packed into a 3D space like a cube of metal or a glass of water. Our equation is rho equals m over v, m being mass, v being volume. The units are kilograms per cubic meter, because the units for volume are cubic meters. Use this when the object's three-dimensional mass distribution is relevant. Things for solids, liquids, gases, usually solids for us in AP Physics. A physics fact you should have memorized is density is defined as mass per unit volume. You can improve that definition with volumetric density is defined as mass per unit volume. Thus, mass can be expressed as rho times v, or density times volume. Next up, we have linear mass density. This is for students in AP Physics C. AP Physics 1, we're not going to have to deal with this, but it's kind of useful to know just for real-world understanding. Linear mass density tells us how much mass is packed along a line. Imagine a long, thin rope or a string. Instead of measuring its volume, we're asked how much mass per meter of length. Our equation is the Greek letter lambda equals mass divided by length, mass per unit length. Think of wrapping a rope around a spool or yarn around a spool. The linear density tells us how heavy the rope is per unit length. We use this when the object's thickness doesn't matter much. I can't move my picture, sorry. Physics fact to memorize for linear mass density is that linear mass density is mass per unit length, and we use it dealing with long objects like the bats in the pictures. Areal density. Areal density, using the Greek letter sigma, tells us the mass per unit area, not volume. We're going to use this whenever we are dealing with things that are thin and flat, like this giant salami. We can find the areal density. Something to keep in mind for both linear mass density and areal density is mass per unit length or mass per unit area is going to remain constant if the density is uniform. So each one of those slices of salami has the same density as long as they were truly equal cut. That ratio is not going to change. Physics E&M students only. Linear charge density, another lambda, is Q over L, where Q is our charge measured in coulombs. We use this when we're calculating electric fields around charged wires. Surface charge density, sigma, is Q over A, right? These are the same ratios that we talked about with linear mass density or areal density. For surface charge density, we use these for fields near charged plates or spheres. Volume charge density, charge per unit volume, used for volumetric charge distributions. And finally, current density, J equals IA. I is our current measured in amperes, and A is the area. So we're going to use this in Ampere's law and magnetic field calculations inside of conductors or solids. Solving techniques for physics problems. First of all, when you're given a problem, our problems are word problems, underline or highlight the important information. Then sketch, which means quickly draw, important information labeled on the diagram. Then determine what you care about. Which objects? Do we care about a start time or a stop time? Write a relevant physics fact. You should have those memorized. And then use a relevant equation. Finally, use math to solve what we're looking for and make sure that your answer makes sense. For a cube volume, a uniform cube that has a side length L and a mass of m, determine the volume of the cube. So first thing we want to do is underline or highlight important information. First, this uniform tells me that it's the same all throughout it. Then we have a side length L and a mass m. Determine the volume for the cube. Now that we have that information, we can go ahead and move on to sketch or quickly draw. So we can just draw our cube and show off our drawing skills. So even though this is really simple of a problem, really easy problem, still get in the habit of sketching or quickly drawing the situation. This is going to help us make less mistakes when the problems become more difficult. Not zero mistakes, but less mistakes, which is what we're going for here. For this problem, we only care about the cube. So why did I even bother sketching it? Because now that I see the cube, it reminds me that this, let's say that's L, and then that's L. So our volume for the cube is going to be length times width times height. And it's a cube, so all sides are the same. So it could be length times length times length, which is just length cubed. Next, determine what we care about. We only care about the cube, I said. Write a relevant physics fact. our relevant physics fact is density equals m over L. And mass can be represented as density, not m over L. Thank you for yelling at me. M over V. Mass can be represented as density times volume. Use a relevant physics equation. Well, that was in our physics fact, so we're good there. And then we're going to use math to solve. To use math to solve here, we're going to make our substitutions. Density equals mass over volume. And we know that the mass of this cube is just m, given to us, highlighted, divided by our volume for the cube, which we determined earlier is L cubed. But because L was given to us as capital L in the problem, we want to make sure that matches. So there we go. Our density equals m over L cubed. Nice and easy. On to a more challenging problem. A uniform sphere mass, or with a radius of r and mass m. Find the density of the sphere. Again, the first thing that we're going to do is underline or highlight uniform. That's a key word that's going to be useful to us. Then we have radius r and mass m. We're looking for density. We can sketch this quickly. R, mass m. That's as good of a sphere as I can do. And that's fine, because this sketch is just for us. So do whatever you can. Determine what we care about. We only care about the sphere here. No start time, no stop time. Write a relevant physics fact. Our relevant physics fact is density equals mass per unit volume. And mass equals rho times v. A relevant physics fact, relevant equation resided within our physics fact again. So we can rho equals m over volume, capital V. Use math to solve. All right, so we know our m is going to be m. The volume for a sphere, this is something we would need to have in our brains. Volume for a sphere is going to be 4/3 pi r cubed. What I want to do is take that and substitute it in for volume. So I get mass over 4/3 pi r cubed. Got that? I'm going to do some erasing here so I can clean this up. Make my answer look nice for that physics teacher who has to stare at it. Density equals m over 4/3 pi r cubed. And that's our answer. No need to go into more simplification, although you can clean it up if you would like. We know that we have a small fraction on the bottom, so that's going to come up here. So we're going to get 3m over 4 pi r cubed. These are the same exact answers. I'm putting a nice circle around it so that teacher can find it. That's it. That's density.